they stay in Africa. Yeah, our next speaker is Professor Mourad Telmini, who will talk about training and research in quantum information and quantum technologies in Tunisia. Back to you, Professor Mourad. Thank you.
Thank you very much. Hi, everyone. I'm very happy to be with you today and to take part to this nice event. And congratulations to our young fellows from Morocco for this very nice organization. So is everything okay? Are you hearing me well?
Yes, I can hear you loud and clear. Thank you.
Okay. Excellent. So just let me share my presentation for today. So my contribution will be about what is going on the ground in Tunisia. I would like to share with you our experience, hoping that it will be useful for everyone here. I will be very glad to discuss with my colleagues about the possibilities of collaboration, also to exchange our experiences so that we can together improve the quantum information and quantum technology training and research and capacity building in our countries. So before that, let me mention this amazing coincidence for this 2021 year. As you can see here, the very unique, actually, position of the digits of the 2021 year is exactly what you need to make the Hadamard plus state, which is very important in quantum computation. So really 2021 is the good year to embark in quantum if you didn't already take this this leap. 2021 is also the year of several initiatives in quantum science. For instance, the Quantum Day, the World Quantum Day initiative was launched like a few weeks ago by a group of 60 plus, more than 60 quantum physicists around the world, including people from Africa and also from Morocco. So that to propose to UNESCO that April 14th of every year becomes the World Quantum Day. And I'm very glad today to see that in Morocco Quantum is organized. So regarding the topic general, and this is a good opportunity to address one of the questions asked the speakers about the definition of quantum technologies. Of course, there are many definitions, but we can agree more or less on this one, is that quantum technologies embrace and include all the methods and say procedures to create tools that are based on the quantum properties of the matter as properties, so namely the quantum superposition of states and the quantum entanglement. So regarding the quantum technologies now, they can be more or less also divided in four major subdomains: quantum sensing and metrology, quantum simulation, and let's say quantum information, including both quantum communication, like quantum key distribution and so on, and also, of course, quantum computing and the quantum algorithms. There is a huge interest, of course, for these topics today. And good news I would like to start with is that in our region in Africa, which is in general absent in in maps showing science and technology in almost every domain. So here in this map you have, as for 2019, this is the counting of downloads by researchers and students of papers related to quantum algorithms. Of course, the main activity here in red is in US and China, like for almost everything, and Europe and other countries, but still in Africa, North Africa, but also in West Africa and South Africa, and probably our countries will show up in the map. People are interested in these domains, and it makes sense for us to be involved in. Well, regarding the funding, many information has already been given, especially by Najwa, but also by Farai. Just to, in a couple of slides, to show how the numbers are evolving very, very rapidly. So this is a publication from 2018, and this is more or less the estimation of the amounts of money for quantum computing. As you can see, the order of magnitude is, let's say, less than a billion per major region: North America, Europe, and Asia around China. Just a couple of years after that, in another publication in 2020, I will not go into the details here, but the global amount is estimated to be roughly more than 20 billion. So we are speaking now about billions of dollars, and every country is putting billions of dollars or euros for US, for Europe, for China, etc. And certainly more money will be put by the government and all the stakeholders actually in quantum. Unfortunately, in this kind of map, you will see also other maps like that. Africa is absent, but our hope, the hope of all of us, is that the situation will change in the coming years. So the question here I'm addressing in this situation and the quantum technology in Africa in general, in North Africa, since the focus today is on North Africa with speakers from North African countries mainly. Even for Farai is from Zimbabwe, and Zimbabwe is at the north of South Africa. So to some extent, we can say that North Africa can include you, Farai, if you don't. Answers to this question, of course, we have seen some of the issues in the previous talks, but let me point out a couple of these answers. So first, on the academic side, I think it is very important to embark in this emerging field to improve the ranking of the African universities and the quality of capacity building and the curricula we are providing and offering. The second one is that the quantum technologies will be really crucial for the economic growth. So it is important to embark as soon as possible. In the following slides, I will say a few words about one of the ranking, the most known ranking systems of universities, Shanghai ranking. And also I will say a few words about the economy here. Just I'm showing a new recent achievement in my country. So regarding the Shanghai ARU ranking, you can see here in this figure the number of the latest issue of the ranking of 2020, starting from 2003 till last year. In Africa, we started with like 4 universities, all of them from South Africa. And today we have, say, 16 universities, of course, from South Africa, but also from Egypt, from Tunisia, and from other countries. And I hope that more countries will join. You can find more details about these statistics in the April issue of African Physics newsletter, easy to find on internet. These universities are contributing to the global effort of research in the world, and also for the publications. So in this figure, you can see also over the last 20 years, say, the contribution of each university ranking. They are like more or less 20 if I gather all the universities here. And the number of publications is really significant. It can be as high as almost 30,000 publications for University of Cape Town, for instance, but also good numbers for other universities. Well, one can say that these numbers have to be renormalized so that they can be compared to the global numbers of the other countries. And this is true. In a slide like this, so using a combination of projection methods for maps, for world maps, and assuming that the area of each country is proportional to the number of publications it produces per year, you end up with this kind of map where you can see that once again it is dominated by US and China, then Europe, and the map of Africa is completely shrunk, as you can see here. And even if I make a zoom, you can hardly recognize a few countries. And this is also a situation to be addressed, and we are working all together very hard towards the improvement of this. So this is one of the motivations. I'm speaking here like as a professor at the university. But most of our countries, for instance, for industry, we absolutely need the quantum, because quantum now is present in every field, like in metrology, for instance. So we are speaking about quantum metrology and industry 4.0, the future of metrology. So we need to enhance the capabilities in quantum. Another reason specific to metrology is that you are certainly aware about the new definitions of the units of the international system for various physical quantities, which is now linked to physical constants, like the ampere is linked to the elementary charge, etc. And for instance, the kilogram is now linked to the quantum, to a Planck H constant, which is not obvious. The second also is, as you know, linked to the atomic transitions, and it is already having a quantum definition. So for competitive industry, you need a good metrology in your country, and for that you need to enhance the capability of the metrology institutes. So you need the quantum culture, you need quantum scientists, quantum engineers, etc. The applications are many. I do not have time here to talk about all of them, but just to give a flavor and just an idea. And the time and frequency metrology is very important for GPS applications, and for instance, and Africa is a huge country. We need a good system for positioning. We are relying on the systems developed by US, GPS, European Galileo, Russian GLONASS system, and more recently on Chinese Beidou Compass. But at some point, we have to develop our own system. Regarding the kilogram, this is maybe more for physics students to see the link between the kilogram, which is a macroscopic quantity, and the quantum constant, the quantum Planck constant H. The link is done through the what is known as the Watt balance, and the current definition of the kilogram is based on the value of H. So it is absolutely necessary to develop this metrology. And at the same time, our countries and our government national frameworks and everything, for instance, here just to give an illustration of the main international agreement about metrology that includes, of course, quantum metrology, the Metre Convention. You can see in this map in red all the member states. And once again, as for 2018, you can see once again that Africa is unfortunately almost absent as we are more than 50 countries in Africa, and you can see here only 4 countries were state members, full state members, and 7 other countries, mainly in South region, as associate states. Well, the situation is slightly improving. So as for today, Morocco, and this is good news for our friends from Morocco. So Morocco finally joined this effort, and a couple of other countries in East Africa are joining as well. But we need much more. We need all the continent here to become red, or at least a mixture of red and pink. Okay, so this is the general framework. So let's speak a little bit about quantum education in Africa. Of course, basic quantum physics and quantum mechanics is more or less delivered in almost all the countries and all the universities in Africa. Here I'm speaking about specific curricula and degrees dedicated to technology, etc. South Africa is leading for many years with the WITS and the agreement with the IBM to use the IBM Q platform, etc. But there are also other initiatives I would like to point out in Egypt, in Alexandria, in Morocco, of course, and the University of Mohammed al-Khamis, and also in my country, Tunisia, in the University of Tunis and Manar. Of course, there are certainly other initiatives I'm not mentioning here, and we can discuss about that later on. But this is just to give you an idea about the situation, where we are, so that we can define where we want to go. To be more specific and to tell you a little bit about what is going on the ground in Tunisia, what we did to embark in quantum technologies, at least at the level of education and capacity building. My university launched a few years ago a master's degree in nanophysics and nanotechnology. In the curriculum for the 3 semesters, as you can see here, some basic courses in black here, and in blue, I'm highlighting more specific lectures more related to quantum science and quantum technology, like advanced quantum mechanics, of course, but also laser cooling and the quantum gases, including Bose-Einstein condensation, quantum information and the quantum computing with practicals and hands-on using IBM Qiskit platform, nanophotonics, nanoplasmonics, nanomagnetism, spintronics, superconductivity, quantum metrology, etc. I will just give some details here about the quantum information and the quantum computing course. We start with a reminder about quantum mechanics, linear and tensorial algebra, the postulates, the definition of a qubit, block sphere entanglement, Bell inequalities, etc. And then we move to the classical information theory. Then start the the core of the lecture on quantum computing with the gates, the quantum gates, various quantum gates, so including C0 gates, etc. And we compare them to classical circuits and the illustration on some simple circuits like the additional. And then we move to quantum algorithms. Of course, the teleportation and the cryptography, very important for quantum communication. Starting from basic and fundamental aspects like the quantum non-cloning theorem to the more practical protocols like BB84 protocol versus classical RSA protocol with and without interception, etc. Then formal algorithms, Dutch, Joza, Bernstein, Vazirani, etc., with various configurations. Before moving to fundamental pieces like the quantum Fourier transform and the quantum phase estimation, so that we can apply them to the stars, let's say, of the algorithms in quantum computing, which are the Grover's algorithm, of course, and also the Shor algorithm for factoring large numbers. So here, just to be more, let's say, concrete, this is a picture of the students we had this year in the final year of the master. There are 12. Here, who is the coordinator of the master. This is also a picture of the practicals on IBM Qiskit. The students, we give them mini projects to develop, and with the topics like Bell inequalities, use of cold atoms and quantum computing, the variational quantum eigensolver, the use of Grover algorithm for satisfiability problems, QFT, quantum counting, computing for finance, etc. And the students at the end of the semester, they present their work, as you can see here. This is a group picture of the cohort. The master is a part of the faculty here in front. Yes, and some of these students decided to continue research in quantum computing and in quantum related domains like cold atoms and Bose-Einstein condensates. Some of you know already Sahar Ben Rashid, who is very active. She is working on IBM Qiskit algorithms for transmon superconducting qubits. Another student, Balqis Nasrawi, is working on VQE, and the third one, Bedis Fadel, is working on coherent transport of Bose-Einstein condensates in ratchet optical lattices. So this is just to give you an idea, a picture about what is really going on the ground. So to support this academic effort, we are also organizing other side events. We started many years ago. You can see here a group picture of a school we organized on metrology with cold atoms and molecules, with the professors from the best universities in the world, from MIT, from etc. And we are also, as we can, taking part to larger events. Here I'm just mentioning the very important Quantum Africa series of conferences, but also to other events around the world. Okay. So all this effort finally had an impact on the creation of quantum community in Tunisia. So after the participation to the Quantum Africa conference, one of our students, Sahar, attended the summer school and hackathon organized by IBM in South Africa. And when she came back to Tunisia, together with a colleague of her, Mohamed Yassine Ferjani, they founded Quantum Q Tunisia, this is also Q cousin like Q Morocco, a branch of Q World, and they organize several events. I'm just listing here a few of them, supported by also events organized by the Tunisian Physical Society. So we start to have a good ecosystem in the country regarding capacity building in quantum. Here are some pictures of the events organized at the university by Q Tunisia. Africa. Okay, so after the first part devoted to the training, I want to tell just a few words, a few more words. I will take like a couple of minutes just to give you a flavor about the research related to quantum in Tunisia. In my own laboratory, Laboratoire de Spectroscopie Atomique et Moléculaire, Al-Sama, in Tunis, University of Tunis, Manar, Faculty of Science of Tunis, but also in other institutions. So we work on several topics, including laser cooling and quantum gases and their applications, quantum registers. Other colleagues are working on quantum dots and 2D materials, including graphene and topological materials and this kind of things. Also photonics and fiber communications, very important for quantum communications, as you know. Quantum gates for circuits, quantum circuits, and also metrology. So to have more details about the laboratory publications and the metrics, please visit the Google titles of some publications. We started a long time ago, more than 15 years now, working on laser cooling, for instance, on atom optics, theoretical study of cold atom beam splitter, deflector of Bose-Einstein condensates, kinetics and the dynamics of Bose-Einstein condensates in blue detuned power low laser traps, and more recently the coherent transport of two species of Bose-Einstein condensates for precision measurements for atom interferometry with direct link and application in quantum metrology and sensing, and other work related to coherent control as well, using ultra short pulses. So that's it. Actually, I was about to finish when I was interrupted. So this is my last slide, and the message here is that we are very keen to exchange our experience, to receive students in our master in Tunis, and also discuss with to improve the capacity building in quantum technologies in Africa. Thank you very much for your attention.
Thank you so much, Professor Mourad Telmini, for this nice presentation. It was fruitful, and it allows or open the doors for future collaboration in Africa, and to build some quantum communities in Africa. So now I will move to the question sessions. So if you have any questions, so please write them down in the chat, and I will ask Professor Mourad to answer them. Professor Mourad, do you hear me?
Yes, I do.
So thank you so much for the presentation. And now I will move to the question answer session. So if you have any question, please write it down in the chat. So Professor Mourad will answer these questions.
So I already see a few questions in the chat section here.
Yeah, here is the question from Usama Huhu. So would you please tell us about the scientific research about quantum-related technologies? Are there experimentalist groups in Tunisia?
Okay, so myself, I'm doing theory and simulation, but of course there are colleagues in Tunisia working on the experimental side. Of course, we are starting this field. We are not leading. We are just trying to embark. So we have all the landscape already mentioned in the very first presentation today. So people working on condensed matter physics, on laser physics, with the techniques including vacuum techniques, cryogeny, nanoparticles, quantum dots. So all this physics is already there and should be improved. We have also research centers. We have also an infrastructure in metrology, and some of the labs are considering to go towards quantum metrology, of course. So we are starting. There are already some infrastructure, but it is still, let's say, embryonic, but it is there.
Okay, thanks. We have another question from Fethi. Can you explain in a few words the quantum metrology?
Oh yes, yes. What is the difference between metrology and the quantum metrology? Metrology is the science of measurement in general. When we speak about quantum metrology, is the use of quantum properties to measure some quantity. And in very few words, the principle is that the quantum states are very sensitive to any interaction with the environment. So if you prepare a quantum system in, let's say, in some state, and if there is in the environment something you can sense, you can measure, like an electric field, a magnetic field, an interaction with the surface, and so on, the state, the quantum state of the system will change immediately. This is what the postulates of quantum mechanics say, and this is how things are going on in the real world. And you can measure the effects using these devices. Of course, this applies for very high precision measurements. You don't need them if you are making macroscopic measurements. Mm-hmm.
Thank you so much, Professor Mourad. I don't know if there is another question or not. I think it's good. So thank you so much for the nice presentation, and we hope to have you another time in the future. Thank you so much, Professor
Sure.
Mourad. Thank you so much.
Thank you.